Okay, so let's discuss the calculations for Lab 9. So in the first part of Lab 9, which is part 1, we are trying to figure out the specific heat of a metal. So as we saw in the laboratory yesterday, we took a metal piece, so this is our metal, and we recorded the mass of our metal. So we know the mass of our metal. Just looking through our data, looking through our lab notebooks, what was the mass of metal that we weighed out in this experiment? What was the mass of metal that we weighed out together in this experiment? 9.9 grams. Okay, perfect. So next we're going to take our metal and we're going to place it in a vat of boiling water. So this is boiling water. What was the temperature of our water that we measured in this experiment? This is going to be the T initial of our metal. What was the temperature of our boiling water that we placed our metal sample into? What was the temperature of our boiling water? (97.1 degrees Celsius). Yeah, the temperature of the boiling water will be the same for all of our trials. Now, in a separate container, we have our calorimeter. And our calorimeter, to our calorimeter, we added a known volume of water. So what mass of water did we add to our calorimeter in our first trial? What mass of water did we add to our calorimeter in the first trial? 48.3 grams, okay. And what was the initial temperature of our water sample? What was the temperature of our water sample? (21.6 degrees Celsius). Okay. So now what we're going to do is, after preparing our metal sample, we're going to take our metal, which is at 97.1 degrees Celsius, and we know that the mass is 9.9 degrees Celsius, and we're going to transfer it into our calorimeter that contains a mass of water of 48.3 grams with an initial temperature of water of 21.6 degrees Celsius. So after transferring our metal block to the water, what's going to happen? So if we transfer our metal block into the water, heat is going to flow from our metal block into our water. So we know that the Q metal is equal to -1 times the Q water. Okay, now what we can do is we can rewrite each of these expressions, considering that we know that Q metal is equal to the mass of the metal times the specific heat of the metal times T final minus the T initial of our metal. And speaking of the T final, at the end of our reaction, not reaction in this case, but after the metal and the water have reached thermal equilibrium, what was our T final? What was our T final for our metal water mixture? What was our final temperature at the end? What was the final temperature after mixing the metal and water? 23.5 degrees Celsius. Okay. Okay, so now we're going to do is we can calculate and we can write out an expression for the heat associated with our metal. We can then also write an expression for the heat gained by our water, which is equal to the mass of the water times the specific heat of water times T final minus the T initial of the water. Plugging this in, we see Q metal is equal to negative Q water. In other words, the mass of the metal times the specific heat of our metal times T final minus T initial of our metal is equal to the mass of water times the specific heat of water times T final minus T initial of water times -1. Okay, so that gives us, for the specific heat of our metal, we get an expression where we have -1 times the mass of water times the specific heat of water times T final minus T initial of water over the mass of our metal times the specific heat of our metal times T final minus T initial of our metal. So plugging this into our calculator, the specific heat of our metal is equal to -1 times the mass of water, which is 48.3 grams, times the specific heat of water, which is 4.184 joule per gram degrees Celsius, times the final temperature, which is 23.5 degrees Celsius, minus the initial temperature of 21.6, over the mass of metal, which was 9.9 grams, I believe. Yes, 9.9 grams, times the not the specific heat, just the T final minus T initial of our metal. So the final temperature of our metal is the same as water, 23.5 degrees Celsius, minus the initial temperature of our metal, which was 97.1. Plugging this into our calculator, the specific heat for our metal for trial number 1 was calculated to be we end up with a specific heat of our metal of 0.527 joule per gram degrees Celsius. Did you receive the same result from your calculator when you inputted it in? And now what you're going to do is you're going to repeat this calculation for the 3 trials and calculate the average. And then you're going to compare this specific heat to the specific heat values given in your table, and you're going to be able to identify the unknown metal because the metal that matches your unknown will have the closest specific heat to your unknown. Does that make sense to everyone? Does that make sense, how to perform the calculations for the first step? Now, for the second example, where we measure the enthalpy of reaction, or in this case, the enthalpy of solution, / reaction. So in the first case, you took ammonium nitrate, and how many grams of ammonium nitrate did we take? How many grams of ammonium nitrate did we take? For part 2, what was the mass of ammonium nitrate? How many grams of ammonium nitrate did we dispense? $10.2 grams. Good, good. We then took our calorimeter and we filled it with what mass of water? So what mass of water did we have in our calorimeter? 9.8 grams, okay. And what was the initial temperature of our water? What was the initial temperature of our water? No, no, no. This is the cold pack. Ammonium nitrate is our cold pack. So the initial temperature of our water is 23.5 degrees Celsius. Okay. So now, as we did in the experiment, we added our ammonium nitrate into our water. And now we have a new solution. Okay. So thinking logically about this, the mass of our solution is going to be equal to the mass of the ammonium nitrate plus the mass of water. Okay, that gives us the mass of the solution of 9.8 grams plus 10.2 grams, which gives us 20.0 grams. Okay, so with that established, I'm going to draw like an imaginary box to represent our reaction. So our reaction is going to exchange heat with our surroundings. In this case, it's going to absorb heat from our surroundings because it's a cold pack. It's an it's an endothermic process because it's absorbing heat. So at the end of our process, we're going to have a solution. We're going to have a solution where the mass of our solution is equal to 20.0 grams, and the final temperature of our solution is equal to what? What's the final temperature for our ammonium nitrate run? What's the final temperature that we got after we dissolved ammonium nitrate? 3.9 degrees Celsius. Okay, so now we know that Q reaction is going to be equal to negative Q solution, which is equal to -1 times the mass of the solution times the specific heat of the solution, which we're going to approximate to that of water, times delta T. So the mass of our solution is 20.0 grams. The specific heat of our solution is 4.184 joule per gram degree Celsius. And the change in temperature is our final, which is 3.9, minus our initial, which is 23.5 degrees Celsius. Okay, so with that established, the heat of our reaction, after punching this into our calculator, we get a value of 20 times 4.184, oops, 23.5 minus 3, oops, 23.5 minus, okay, punching this into our calculator, that gives us a heat of reaction of 1,640 joules. And we know in 1 kilojoule, we have 10 to the third joules. So we have an enthalpy, a heat of reaction of 1.64 kilojoules, positive. That means we're absorbing heat. That means we're absorbing heat. One moment, I'm just adjusting the chat. Okay, so now that we have the heat of reaction, we can calculate the moles of ammonium nitrate that participated in this dissolving process by taking 10.2 grams and dividing by the molar mass. So we know in 1 mole of ammonium nitrate, we have how many grams? In 1 mole of ammonium nitrate, we have how many grams? What is the molar mass of ammonium nitrate? .0 grams, yep, perfect. And that in turn gives us, for the moles of ammonium nitrate, we have 10.2 over 80.0. That gives us 0.1275 moles of ammonium nitrate. So then we can calculate the enthalpy of solution. And calculate the enthalpy of solution of ammonium nitrate by taking the heat of reaction over the moles. So we get 1.64 kilojoules over 0.1275 moles of ammonium nitrate. And if we punch that into our calculator, we have 1.64 over 0.1275. That gives us 12.86 kilojoules per mole of ammonium nitrate. So not the most accurate determination, but this is how you'd calculate the enthalpy of solution. Does this make sense to everyone? So for each of the reactions, for the hot pack and the cold pack, I'd like you to generate a plot of temperature in degrees Celsius versus time in seconds. I'd like you to clearly identify in the plot the T initial and the T max. So for example, if our plot looked something like this, the T initial would be here, and the maximum temperature would be here. And then from the T initial and T max, I'd like you to calculate the delta T, which is T max minus T initial. And if the delta T is greater than 0, then it's an exothermic reaction. And if the delta T is less than 0, it's endothermic. The hot pack calculation is problematic because the thing that's absorbing the heat is the hot pack contents. For the hot pack, you don't have to worry about making a detailed plot. Just plot as many data points as you can up to the maximum temperature, just to make sure that I can see that you know how to plot temperature versus time and read from the plot the initial temperature. As the hot pack example, as they're slow release hot packs and it was still heating for a fair amount of time after we ended the recording, that data is found in the Canvas page titled Laboratory Recordings. Yes, I provided the maximum temperature for the hot pack, but you don't have to do an enthalpy calculation for the hot pack because it's hard to define. We don't have the heat capacity of our hot pack contents. So we can't complete the calculation since we don't know the specific heat of the hot pack contents that are being warmed. Yes, I'd like a scatter plot for both temperature versus time for both of our runs. The key feature I just want you to be able to identify is whether a process or physical change, be it a reaction or a physical change, is exothermic or endothermic as a result of a plot of temperature versus time. For ammonium nitrate, I do want to see an enthalpy calculation, and I do think, and I strongly recommend that you be familiar with those enthalpy calculations, just like we did in lecture. Does that make sense? Yes, and all of the data as well as the lab recording is on Canvas on the page titled Lab 9 Recording. 2 different graphs, please. 1 for each experiment. Yes, the calculation for the cold pack, which we just did, is what I want to be able to see in your report. The hot pack, we don't actually have enough information to complete the calculations beyond just calculating delta T. So that's it for the calculations for the calorimetry laboratory.